So there are just a couple of concepts in 8.2 that I wanted to pull aside in a video and clarify. And the first of the topics is the squeeze theorem for sequences. If you have three sequences, and for each element in those three sequences, if you have a sequence, for instance, an, bn, and cn, and for each of the n integers in that sequence, if the bn's fall between the an's and the cn's, so in other words, if the sequence is sandwiched and both the outer sequences converge to the same limit, then so does the inner sequence. So graphically, you might see something like this. If I were to graph a sequence and let me use a different color. So say this is a sequence here. I'm having trouble here. Here we go. And let me grab another color. So let's say that's the AN sequence. And if we have another sequence, CN, and in the middle is your BN, and this sequence converges to L, and this sequence also converges to L, then because BN is between it, it also is going to converge to L. And that's the squeeze theorem, and you may have seen it in Calc 1 when you did limits, or maybe not, but the squeeze theorem for the sequence is the same exact concept that we did with the squeeze theorem for limits. So the next concept is a theorem that is somewhat intuitive, and that is the theorem that states that it's basically called the bounded monotonic sequence theorem, and states that a bounded monotonic sequence converges. So in other words, let me write a little something down. So if we have a bounded sequence, let's call AN, and its every term is less than or equal to some upper bound, for instance, and the sequence is either monotonically increasing or decreasing, then it's going to converge. So it's going to converge to something. So a bounded sequence that's monotonically increasing or decreasing is going to converge. So that's the second point. So if this thing is bounded and it's heading in decreasing every single term or increasing every single term, and it's bounded, it's going to have a stopping point. And that stopping point will be the convergence point. So that's kind of a common sense theorem. And this last concept is a very important one, and that is the growth rates of functions. And I wanted to look at a theorem with you. If you're given two non-decreasing sequences of positive terms, so you're going to be given two non-decreasing, so two non-decreasing sequences of positive terms. Finish this video up before my battery runs out. Given two non-decreasing sequences of positive terms, we'll just call them AN and BN. Okay, so we have these two sequences, and the question becomes, which sequence grows faster as n goes to infinity? And you already have somewhat of an intuitive feel for this. If I were to ask you which function, a log function or an exponential function, grows faster, I think everyone would know that a log function grows slower. So you already sort of have a concept in your mind And let me first draw upon that before we go to the theorem. My stylus is... Okay. So you already know that a log function is going to be slower growing than, say, an algebraic. Some x raised to something. And you would know that an algebraic is slower growing than an exponential function. And you may or may not know of the tower function, which is sort of the king of all kings. That's the king function, right? N raised to the n is going to be the fastest growing. The one that you may not be as familiar with is the factorial function, and where does that fit in? So let's go through the theorem, the formal theorem, and we'll lay out the growth rate for you. So again, here the log function is going to be the slowest growing function, and here we're going to just say P and Q and S are all positive real numbers. Okay, so your log function, and it could be the log of n raised to any power, Q, is going to be this is slower growing than an algebraic. So here's your algebraic, right, which is n raised to some power. Here's your log function. And then if you multiply those two together, that'll be slightly faster in growth than just a pure algebraic or a pure log. So this is just a log times an algebraic. I don't know why this is not. There we go. And then here, if you have P and S together, you if you add those two exponents, that's going to be even faster growing. So the key to understanding this algebra is that P and S, right, and S is it's greater than just the algebraic n raised to the p. So you're adding another exponent to it. And then here's your exponential function. And now here's a new one. That's your factorial. And we're going to be doing quite a bit with that. So that's where your factorial function, or your factorial sequence, falls. And again, your factorial is 1 times 2 times 3 times 4 all the way up to n. And then here's your tower function. So you can certainly put this on your formula card, but you really do need to memorize it. So you need to have this committed to memory. That indeed your log is slower growing than your algebraic, which is slower growing than your exponential, which is slower growing than your factorial, which is slower growing than your tower function. And that's a wrap up.